Okay, so thanks everyone for coming. Today's speaker is Dave Kuhl from NRL. And so Dave received his master's degree in aerospace engineering from Virginia Tech in 2001, and then his PhD from University of Maryland, College Park in 2009, with a dissertation on data assimilation of trace gas retrievals in NOAA's GFS with an LETKF. And after that, he went to NRL in DC in 2010, where he worked on improving troposphere to thermosphere data assimilation within the Navy's various global operational NWP models. And currently, he is a PI of two major projects, one with the development of an operational assimilation system for the thermosphere and ionosphere, and the other with improving the weather and aerosol forecasts of the operational mesospheric ESPC atmospheric model for Air Force hypersonic testing. And so today he will talk about the kind of overview of Navy's future ionosphere and thermosphere data assimilation. So go ahead.
Thank you very much. Thank you everyone online. I think you can hear me. Let me know if I have any problems here. So yeah, I've got two projects that I'm PI of. This is the one on ionospheric and thermospheric DA. And obviously, I am just one person. There is a lot of people behind me that are working on this. And yeah, I couldn't do any of this without any of these people. So big kudos all around for that. So the goal of this particular project is improved operational analysis and forecast of the ionosphere and the thermosphere. And the objective for and that particular goal includes actually three different projects. There's mine, which is the data assimilation part. Then there is Sarah McDonald, who has the ionospheric modeling part. And then there is Steve Ackerman, who has the thermospheric modeling part. And so we all work together in order to get this goal. The objective from our part is a fully coupled ionosphere thermospheric data assimilation system. And the concept there is that neither the ionosphere nor the thermosphere, especially the thermosphere, does not have enough observations on its own. And in order to constrain the initial value problem that is the ionospheric modeling system. And so we need to be able to use ionospheric observations in order to constrain the thermosphere. But similarly, we believe that by using thermospheric observations to constrain the ionosphere, you also add skill to that problem. So, so sort of pictorially, what we're going for is this coupled neutral ionospheric data assimilation system. And of course, I think most everyone here is data assimilation people, and the data assimilation problem is you take old information, which is your prior, which comes from a forecast of some type. You have new information, which comes from observations, and you combine that together with error estimates. And the error estimates are from the observations as well as the prior forecast, and that gives you the analysis as well as analysis, and also, especially in the ionosphere, it gives you a parameter estimation as well, which I'll talk a little bit about later. And so for our particular system, it's a combination of the neutral atmosphere models, and I'll be talking about these along the way. And so the neutral atmospheric models, we start with NavGen and Neptune, which are basically our NWP models that we run. And for the troposphere, we have a NavGen MA, which the MA stands for middle atmosphere, and that is run with an ESPC system, which is called the Earth System Prediction Capability. And so it's not just one model, it's not just an atmospheric model, but it's a coupling between the Navy's ocean model, the atmospheric model, a waves model, and an ice model. And then that one goes up to about 115 kilometers. And then what we've been developing over the years is this NavGem HA or Neptune HA. So that goes up to around 500 kilometers. And the way that we have it right now and currently for the model is that it is one-way coupled to the ionosphere. So right now, the thermospheric model drives the ionosphere. We are shooting in the long term in order to have two-way coupling between the two. However, these are two pretty major systems, and getting those things coupled is quite a feat. And that's out of my area because I'm the DA, so I can only do what I can do on the DA. I can tell you though, for the NavGem and Neptune HA models, you have to have some sort of ionosphere in there because you have ionospheric heating that comes from those constituents. And so what we use right now is an IRI. IRI is within the model in order to give that information. And as I said, that's one-way coupled to the ionospheric model. In the ionospheric model, we're in a transition. As always, there's transitions when you work in a NWP center. So there's SAMI 3, which is running right now operationally. They're going to SAMI 4 very soon, probably by the end of next year. And then maybe in a year or two, maybe 2 years, we'll get into NRL SAMI. And so again, this is Sarah McDonald's group. They're working on improving the ionospheric model as well. I've also put onto this plot the various observations that fall under the thermospheric observations and the ionospheric observations, and I'll talk to those in a second. So, the model configuration differences between the regular, which I call low top, which would be the NavGem or Neptune right here. Also, I should say here, okay, NavGem is our current operational NWP model. Neptune is the future operational NWP model. And as far as the low top model, we're actually in the middle of that transition right now. We're running both of those models at the same time. It's kind of a weird thing that normally doesn't happen at operational centers because it's so costly to run these models. But you can't turn off the old one until the new one is proven 100%. And we're sort of in that situation. So like everything, when you're in that situation, you have things that cross over. But what I want to say is that from NavGem, which is the deterministic NavGem, the short one, NavGem MA and NavGem HA, they're actually all exactly the same model. We haven't developed three completely different models. They're one executable, and all you do is have nameless flags that you put in there in order to change it and raise the top of it. And there's several reasons for this. We aren't a huge group like what NOAA and ECMWF and UK Met have. And it's hard to keep up three completely different models. So one is you just keep up one model. The other thing is that the system is designed so that each vertical extension does not degrade the forecast skill of the lower regions. So we've spent a lot of years in order to get this really good skill in the troposphere. And what we do with these extensions is that we want to improve the skill up here, but we don't want to degrade the skill down there. And so that takes a lot of time and effort. And similarly, when we add on the HA, we do the same thing. So just to give you a picture of, as I said, we're in the middle of this transition. NavGem, there's actually two models that are being run. One is this NavGem deterministic, which is the 65-kilometer top. And as I said, at the same time, we actually have Neptune running at 65 kilometers as well. This one will be turned off probably in 2 years, I'm thinking. Hard to say, though. We have the second model, which I said, which was the ESPC, which was this coupled model, and that has NavGem MA with the 115-kilometer top. And both of these systems actually run with NavDAS-AR, which is a hybrid 40 VAR system. And that was a system that was developed over many years. I was part of the group that hybridized it in ensembles. The Neptune DA system is actually not turned on yet because we're in this in-between period, and Neptune is actually being initialized off of the NavDAS-AR analysis. But in the next year, we're going to be turning on the Falcon DA, which is a JEDI DA system. And they've been working on that since, I believe it's 2020. So they were part of JEDI very early on, along with a lot of the other operational centers. And the plan is to transition a 40 VAR system. The future system, which I'm talking about here, is this Neptune HA, which goes up to 500 kilometers, as I said. The model there is Neptune HA, and the data assimilation system that we're planning for that is JEDI LETKF. And we have that running right now, but it has quite a few years of work in order to get it up to operational standards. So the first generation of DA on the thermospheric side was the Neptune HA LETKF. And this is currently running in hindcast mode. It's not operational, but it's on our computers, and we use it for scientific purposes. It was built for this DARPA Sea project, which concluded in 2023. We keep this running because it's very important for our development of the next system that we're having. The model, as I said, was Neptune HA. The DA system with NavDAS-AR, which was the NavDAS-AR, if you saw from the previous one, is a hybrid 40 VAR. And we reformulated it to be an LETKF. This system is not JEDI. One of the things that I have to say here is the whole reason of why we didn't go with the variational data assimilation when we were raising the top of NavDAS-AR. And there's quite a few different reasons for that. I think really for me from the DA standpoint is that these models, this Neptune HA and Neptune HA, are very green. They're very new models. We have only been running them for a few years relative to what I'm used to, which is down here, and they are changing dramatically as far as the chemistry, as far as dynamics and heating. They find issues, they have to attack those issues, the whole model changes. So if we were going to go after like a variational system, and what we'd obviously want to go after is a 40 VAR system, then you would have to develop a TLM and adjoint. And if you're trying to develop a TLM and adjoint with a model which is completely being rewritten, sometimes every 6 months, that ends up being something that, as far as from the data assimilation side, it's untenable as far as trying to hit something operational. So that's why we went with the LETKF in that particular respect. And there's several other reasons, but that's the main one. So when we set up this system, we set it up to assimilate all the NWP observations, which is about 4 million every 6 hours. It takes in the real-time MLS, SABRE, Meteor Radar. It takes in the MIGHTY and the GOLD. And we didn't have it come in with the SSMIS UAS. That was a radiance. So we never got to that point with that particular system. So that's the first generation that we have running. The second generation that we're shooting for is this Neptune HA Falcon LETKF. I call it Falcon because we're really basing it upon the backs of all the work that they did for the past 5 years in the troposphere. So it's currently being built for operations. The model is Neptune HA. The DA is going to be a Jedi Falcon DA and reformulated to the LETKF, exactly for the same reasons that I was speaking about beforehand. This Neptune model is changing very, very quickly, trying to get the best model that we can. The observations that we're shooting for, we're going to try to put in some radiances in with an LETKF. For all of you here that are used to LETKFs, know there are issues with assimilation of radiances, and it's not that it can't be done, but it needs to be done correctly, and it takes time. We're hoping on getting there. I don't know how long it's going to take. And then we want to try to take in all these mesospheric and thermospheric observations that we can. And I'll go through sort of why each of those. Now let's look to the ionosphere. So the ionosphere, the current and near future Navy operational systems currently running right now is NEMO 1.1.3. As I said, that model is SAMI 3, and the DA that they have on that is this IDA 4D DA system, which is actually a 3D vault with NEFGAP. This is developed out of APL. The next system, which is going to be turned on operational, is NEMO 2. That is slated for sometime in FY26. The model there is SAMI 4, and the DA system is Anchor, which uses a Kalman filter. I'll discuss, I think, the next slide, what Anchor is. The future that we're trying to get to, and what we've been working on with Jedi for the past year, is this Jedi ETKF system, and that uses this the new model that will be coming down NRL SAMI, and I'll talk about this. Might possibly be informed by the Anchor solver. So the first generation is this Jedi ETKF that we're developing. It's a state space solve using ion densities and geomagnetic coordinates, plus the driving parameters. The way that we have it set up right now in Jedi is that there is open to the public running with PyIRI. We can't release our SAMI codes to the public because they're operational Navy products. So that's why we have developed it so that it works with the PyIRI. But you can check out, if you have internal Jedi privileges, you can check out that system, and we have it set up, and we've been doing runs with it with NRL SAMI as well as the PyIRI, and we're able to assimilate with these driving parameters, which can be like F10.7, but also can be winds and other things. I'll talk about that a little later. The observations that we're feeding into this is electron density profiles and tech. And the system that we're using is an ensemble transform Kalman filter, which is a global solve of state space. So the second generation is using this Jedi Anchor system. So the Anchor data assimilation system was developed by Victoria Forsyth out at NRL, and it's this stepping stone that we had between the IDA 4D and the Jedi ETKF. And she put together this amazing system, which has worked very, very well. I certainly had my doubts at the beginning, but she has proven it, and the statistics are there proving that this system really does work very well. And I think there's some very good lessons to be learned from the system that she set up. So Victoria is going to give a really good talk on this on Thursday, but I will give you a short idea of what's going on here. Maybe some of you already heard this, but so basically this would be an electron density profile. And what she does is that she breaks up the electron density profile and decomposes it into, for this example, she has 6 anchor parameters. One, which is HMF2, NMF2, HMF1, NMF1, HMFE, NME, okay? And then she uses functional relationships in order to fill the curves between these particular points. And And so what this does effectively from the DA standpoint is that each of these variables then end up being a 2D surface, okay? So as opposed to having in ion density space in a geomagnetic coordinate system where you have this 3D grid that you're solving, she has now broken the whole problem down into 6 2D surfaces that you're actually solving for. And the other side of this problem is that you then have to take your observations, which you would have an ionosonde, or you would have Cosmic 2 tech, or you had ground-based GPS, and you have to then take those measurements and turn them into these anchor parameters. But with that, she has actually reduced the space so much so that she can actually solve it using a Kalman filter, and which was pretty amazing. Now, what we hope to do in the next year is take her system and put it into JEDI. And what the plan is to start off using a local an LETKF with the system, and which should be very, very fast to solve, and I think should be very comparable to what she has with her her system. But it really, I can't say enough, this was a really interesting way of doing things, and you can read her paper down here and listen to her presentation tomorrow. So then we get on to the third generation, which is sort of this, I'm sort of calling now a JEDI hybrid, but we're going to have to put these systems together. So another thing that ends up when you do this, of course, is in the anchor space, you basically get rid of all the wiggles. Okay, there's nothing in between these lines other than functional relationships. And some people in the ionospheric modeling world believe everything is smooth, and smooth is what everything should be. And some people believe that that's not true. And I don't know. I'm not an ionospheric modeler. I'm a DA guy, and I'm just trying to get the truth. And but that is one thing that ends up happening, is that you end up with a very, very smooth state. So we're going to do head-to-head versus these two things, and possibly the state space might be a combination of ion densities and anchor points. You can simply do this by taking your state vector and say you have a state vector in ion density space, and then you have 6 parameters. You just slam them onto the end of your state vector, and you can have observations that can be in that space that would solve to that, and you can have observations that are not in that space, in the ion density space, and you can solve for that when you're dealing with ensemble type solves. So anyways, that's going to be what we're looking at next. So that's sort of the roadmap from that. So that ends up giving me these two sort of, now we're getting the 30,000 foot look. So on the left here, the implementation of JEDI Thermosphere coupled to JEDI Ionospheric DA, which is raising the top, okay. I got these all messed up. I think implement JEDI Ionospheric DA, implement JEDI. Oh, I got it. Okay, so we'll start over here. So we're going to implement the JEDI Ionospheric DA just on its own. We're then going to implement the JEDI Ionospheric coupled JEDI Thermospheric DA. So we're going to, in this particular instance, we're testing a lot of things that we have problems with. Time windowing size. We're going to look at the anchor point versus other assimilations, and adding in ionospheric observations. Then we want to start bringing in thermospheric observations and seeing if we can start extracting thermospheric, using thermospheric observations in order to help constrain the ionospheric problem. On this side, it's raising the top of the Falcon DA system and turning it into an LETKF system, and then adding in these thermospheric observations. That's what we're doing up here. When we go down here, we're then adding on the ionospheric observations alone and seeing how those use the coupling in between those systems in order to help constrain the thermosphere. The last one is when we turn on the fully coupled system where you have a single state space solve of the ionosphere and the thermosphere together. The truth is we might be okay with our solution of either of these two, and we may not have to get to this point. But the truth is that if you don't design the system for fully coupling, you never get there. And so you have to start very early. And so that's why we're designing it this way. So that's the 30,000 foot about where we're going. I'll stop here and sort of take questions about where we're going with this. Is there anyone that has any questions so far?
David, what is the typical data simulation window for your ionospheric data simulation for NCAR?
Okay. Right now, what they have is a 15-minute time window. The problem is that the observations that they use have, a lot of them have a 20-minute to 45-minute time delay. And if you have a 20 to 45-minute time delay, in my world, that's insane. And so what they have to do is they have to go back 2.5 hours and then run these small 15-minute time windows, even though you're here. So you have to make this DA system that goes really, really fast, that can sort of catch up with 5 times in when you're trying to solve here. So that's why there hasn't been a lot of window size versus time delayed observations and quality of nowcast as well as forecast from that state. And that's what we need to do.
Okay. Second question, how you will manage background error covariances for electron density profiles?
Yes.
With the NCAR specify analytical function?
Yes, that is a great question for Victoria. She's been working on that and thinking about that. And
I will ask.
Yeah, ask her that. She loves that question. And yeah, this is why I rely on, I don't know all the answers.
That's fine.
Yeah. Yes.
So when you simulate anchor points,
Yes.
does that mean that you only care about the displacement of the model layers, but between layers, the profile of electron density, you just let model to take care of that. You actually don't care anymore. Or you just, because you are simulating those anchor layers, it more define where those layers are, right?
Yes.
So the profile in between, you actually don't assimilate any information anymore.
Yeah, you're totally, and I think the argument is that for like take for example an ionosonde, is that the argument is that I think, again, this is a good question for Victoria, is that there isn't any information about the in-between from the ionosonde. The ionosonde only gives you this peak value of F2 and only gives you the HMF2 when you have that little curve in there where you can sort of mount. And so that it's sort of like, well, we're making it up anyways.
So you don't know the profile anyways.
You don't know the profile, and so, you know.
So why assimilate them?
Yeah. Now, I would say that there.
You have background profile, so you need to take care how to basically manage your background profile.
Yes, exactly.
Data which doesn't have vertical information.
Yes. So that's why I
This
said.
is exactly about question how you will manage background error covariances.
And she's got
It's exactly the same question.
Yeah, exactly. And that's where you get into all the sticky and nasty stuff.
No, it's possible. It can be done.
Yeah, exactly. And I think they have a good system. Again, I'm still interested in being able, and again, I can't say enough with JEDI is such a cool and great system for DA because we can do apples to apples comparison. We can use the exact same observations and we can set it up and we can build an anchor system and we can build an ETKF system and we can just, okay, let's see what happens there. And this is, I've never had that before.
And you can do observing system simulation experiments.
That's exactly right.
Knowing nature truth, and you
Yeah.
can compare it to algorithms.
Exactly. And so we can start, and so, yeah, I'm very excited. Anyone online? Anything here before I go on? Okay, so now I will dive into observations, because we're setting up this new system and data assimilation. If without observations, we don't have anything. And so basically there's three uses of observations. There's operational data assimilation. That's obvious. We need our observations. We need them in fast enough time so that we can do our operational data assimilation. So that's the simple one. The second one is scientific purposes. So scientific purposes fall under a couple things. So one is you can have observations that have not been operationalized. So we're getting observations, but they're not being downloaded fast enough for us to use. But maybe that type of instrument will be used in the future. So they put something up, so, but maybe we'll be able to get it faster or something similar to that in the near future. So from that particular standpoint, it's you put them into your system. And of course, I'm only talking from an operational standpoint, because that's where my head is at. Use is that, we're pulling them in because we might have a future system that looks somewhat like that. And then the third one is verification of the developing DA system. If you have to have truth, and observations are truth. And so the way that that I like to do it, and I'll talk about this a little bit further, is that putting the observations into the data assimilation system allows you to use them for verification. And so, yeah, that's the three different ways that I look at the observations. So I looking at the availability, and these are the observations that I'm going to be talking about. Yellow is operationally available and working, and we're working on JEDI in gestation. Green highlighted is not operationally available, but potentially it could be available if the right instrument was put up on the right satellite. Magenta highlight, not operationally available, but we use this for verification. Red highlight is currently operationally available, but soon to be decommissioned. So let's start stepping through these. So I'm going to start down here. This is the NWP observations. We've got about 4 million every 6 hours. Now, the NRL Falcon Group, as well as many other NWP centers, have been working with JEDI for the past years. I don't know, 10 years JEDI has been around now, 15 maybe, I don't know.
We started from scratch only 2017.
17. Okay, so that's 8 years. 8 years. Okay, there you go. So they've been working on getting these observations in. So they are operationally available. The observations are tropospheric and stratospheric observations. They contain conventional retrievals and radiances. They're already read in within JEDI IOTA, and they already have observation operators in there. So this is a great set that we have. We move up, NRL MLS. So NRT. So NRT stands for near real time, and there's also a scientific product of MLS. So the near real time comes out, I think we can get it like 4 hours or 5 hours after it's actually measured. The scientific product, I think, is like 2 days. It's operationally available from NASA. The observations are temperature, ozone, and water vapor. We're working on reading retrievals of it into JEDI IOTA, and we're looking at doing retrieval assimilation of the NRT MLS. The problem is the MLS will be turned off in around 2027. There's been some people pushing. My boss has been trying to get it extended. It's a very important middle atmosphere observation, and but it is very useful for verification, and we have used it for years and years for the temperature, ozone, and water vapor in this region of stratosphere, mesosphere, and into the lower thermosphere.
What satellite is it on again?
Aura. Thank you. I know someone in the room should know these things.
Isn't there microwave limb sounders on the Air Force satellites, DMSPs? Are they also going away?
If they're on there, I'll have to look into it. If they're on there, they don't have anything in the middle atmosphere that they're looking at. Yeah, I would know if they had anything in the middle atmosphere. Yeah. Next one is SABRE. So SABRE is not operationally available. It never has been. The observation is temperature. The read-in is we're working on reading into Jedi Iota. We're working on retrieval assimilation. Both of these things are very easy, and we've been using it for years for verification. It's above MLS, but it's a very good, 110 kilometers, somewhere around that area. Very good verification data set for us. Meteor radar. So we've been working with Noah Peterson at University of Colorado, as well as we've been working for years on running with meteor radar assimilation within our different systems. And we're working on getting it operationally available through GTS. We're hoping that we can get that pushed in by February of 2026. The observation is UV winds. We're working on the read-in into Jedi Iota. And again, it's a retrieval assimilation, so the HFX is pretty straightforward that we have for that. So that's another one that we're hoping on getting. SSMIS UAS. It's operationally available from DMSP. It's a brightness temperature reading. It's we have been working with Francois V. What's Francois V's last name? Yes. He was helping quite a bit on getting this in there, and it's a radius assimilation. It uses the CRTM, and it has some slightly different calls, which is why we needed to work on that. But we've got it in there and we've been running with it. Problem with this is by 2027, it will be turned off as well. However, there are some other instruments that are kind of like it. There's this JPL Easy, which might be a replacement for it, and some other
APL.
APL. Okay, the people I've been talking to is at the JPL.
No, I understand, but it's an IPL instead.
It's an APL. Okay, thank you. I'll fix that before tomorrow or Thursday.
SEMI is a
What's that?
SEMI is PI.
Oh, okay. There you go. Thank you very much. But we've started looking at that data, and it seems to be pretty good data. And I don't know if it's as good as what SSMIS UAS, but we're looking at that. There's the UV instruments that the O, the N2, and the ON2. We're working with Clayton Cantrell at APL. These are not operationally available right now. The ones that we're working with is the Suzy and the Suli. And this is all sort of, for assimilation of this, we need a lot more research. The read-in, we need to look in how that's going to go. The HFX, we need to work on how that's going to go. I know with IDA4D, they do a radiance assimilation. So that would be interesting, trying to get that into Jedi. There's also other new UV observations that I know several people at NRL are working on instruments, like on ISIS. But anyways, we don't have enough observations. We got to look at whatever we have. So that's what we're looking at. We're starting to look at. That's pretty early on. Mighty. This was Icon Mighty. It is not operationally available. It flew on the Icon satellite, and from October 2019 to November 22, it has UV winds. I think they're very good. We assimilated them and we still are assimilating them when we have them in these time periods with our NavGem HA system and the LETKF, I've gotten some good results from them, but we do use them for verification too, and they're a great use for verification as well.
And are they at 200 kilometers?
No, so
the
they
meteor radar.
So it starts at, so the green goes down to like 105, 10, something like that, and then it goes up. the green is lower, the red line, there's a green line, there's a red line. The red line, I think, goes up to 300. Yeah, somewhere around there. A little bit wider layering on the red. But yeah, it's an area we don't have much information from, so anything we can get is good. And so we're hoping on another future, but I don't see any future mighty instruments, but maybe someone does. No, I don't know. Gold. So I believe Dr. Lascar is actually on the call. I saw him join. We've been talking to him about gold. I think it might be operationally available. There might be a little bit of work in order to get it into our system at FinMOC. I don't know. The observation is temperature. We're working on the read-in observations into Jedi Iota, and we're going to start with a direct assimilation of the product, which is not a good way to do it. That's what we did before. But what we really want to get to is the assimilation using averaging kernels, which Dr. Lascar has several papers on, and I think there's going to be a good future for that. So this is one of the observations that we're working on. Another observation we're working on is satellite drag, and Nick Dietrich, who joined us at NRL last year, has been working on that problem, and so he's going to be presenting. I don't know if we're using this acronym for the Community Space Weather Modeling and Data Assimilation Workshop.
Oh,
Well, I didn't want to write it all out, and so I just put the acronym down. So anyway, if someone gets a better way of putting it on
well,
slides,
it's not a better name. This is hard to spell.
yeah. So anyway, Nick is going to give a much more in-depth operationally available. Yeah, there's various satellites that we could potentially get, pull it down. The observation is position or density. We're working on how to read it into Jedi. I think that would be pretty straightforward. And Nick's been working on several forward operators. The assimilation of the densities, which might not be operationally available, or the assimilation of the satellite locations. Anyways, we're looking. This is one of the ones that we're looking at, and it would help us give us a constraint on the upper part of the atmosphere. So that's why we're looking at it. So now we go over to the other side. So now we're in the ionospheric observations. So for the ionosons, actually John Hydacek and Hui here are also both giving presentations. I think, is yours tomorrow or on Thursday?
Well, Jedi is more Thursday.
Okay, Thursday. So
John is Thursday as well.
yeah, John is definitely Thursday. So they're going to be talking about what we've done on the ionoson assimilation. Operationally available, we've been actually having a lot of problems with the feed of the ionosons, and I don't know where it's going to be coming from, and they've had issues over the last year. The observation that we first start with, as I was talking about before, is this electron density profile assimilation. The EDP is read in by Jedi Iota now. We're working on we have an working interpolation in Jedi. We're working on the Jedi UFO interpolation system. And the future research, as I talked about before, is anchor point assimilation of ionosons, possibly using trace assimilation as opposed to the EDP. Go back one step from that. There's this trace assimilation. Maybe you can get more information there. And then the longer term, whether or not you could do ionogram assimilation from just the pure ionograms. So we're looking at all of that. And that's probably the direction of increasing complexity and when we're going to hit it. The next one is the ground-based GPS. John Hydacek is going to talk about this in his presentation. And this is where he's been working with a nice interpolation program, which is very quick and can slice through the atmosphere and give us basically a trace from the ground-based station to the satellite. And the observation is total electron content. The read-in is the vertical tech. Vertical tech we're just doing as a practice for the system, but what we want to get to is the slant tech. Also, we can use the vertical tech as verification, actually, which is really good for that. The HFX, we've got the vertical tech working, for interpolation in JEDI and working on, again, the JEDI UFO. The slant tech is working, and we're working on the slant path interpolation into the JEDI UFO. So the future research on this is the anchor point assimilation of it. But we've actually made a lot of progress over the last year. We've made a lot of progress over the ionosondes as well as the ground-based GPS assimilation. The UV radiance retrievals from the ionosonde. This is another thing that we're working with Clayton at APL. Operationally available, no. Again, this is coming from the Suzies and the Sulis. And as I was talking before, I think probably the easiest one here, because Victoria's already done it, is the anchor assimilation of these of the retrievals that are coming off of this, and that's probably what we'll try first in JEDI. So we're working on reading the retrievals. We're working on the anchor point forward operator. We're also looking at this assimilation of the radiances, like I said, like what they do in IDA4D. And then obviously we're looking at new UV observations, which might be operationally available in the future. So that's the UV radiances. Finally, we get to Cosmic 2. Did a lot, again, these three, Cosmic 2, ground-based GPS, and ionosondes, we did a lot of work over the past year with this. John Heinechek is going to talk about it in his presentation. Operationally available from UCAR. The observation is tech again. We've got the read-in of tech into JEDI IOTA. We're working on the SAT-to-SAT path interpolation into the JEDI UFO. Future research of anchor point assimilation at the midpoint with JEDI. And then this is a new thing that Nick and Hui are looking at, possibly bending angle assimilation. And you can talk to them if you're interested in finding the what they're thinking about there. But that's another way that we might be able to do Cosmic 2 or the ground-based GPS. It's more ground-based GPS or is more Cosmic 2? Cosmic 2. Cosmic 2.
Different matter.
We don't think we're going to, okay.
No.
No. So yeah. So that goes through all of the observations. Sorry that took so long, but I thought that's what we're doing right now. We're building a JEDI system. We're trying to throw the observations. That's what takes a lot of time and effort, and that's what we're doing. So I use JEDI in two modes. So the first mode is this data assimilation mode, which is pretty obvious. You're trying to get the data assimilation done. The second is this observation verification mode. And I think this is another really big, useful thing of JEDI. So the observation verification mode basically uses several steps. You use the JEDI IOTA observation read in into IOTA. So then you have the observation in IOTA file. Then you use the JEDI forward operator for a model to pull in your model and forecast and do your H of X and then put that into IOTA as well. So basically what you could have is you have all the observations, you have your analysis at those observation points, you could put your forecast at those same points, and then you can feed that IOTA file, or sorry, Yoda, you guys are all JEDI people. And you can feed that into Met software and you can do your statistics off of that. And so what is brilliant about this is that it fulfills my long lost want and need that every time I put in a new observation to my DA, I can use it for verification. And I don't have to spend twice as amount of time trying to build a verification operator as well. And so I'm really excited about this. And we've been using this for the ionosondes, very useful, and it looks like it's working very nicely. So, and then of course, then you have the same forward operator as the DA. So that's great for VNV as well. So, so those are the two modes. So now we'll talk a little bit about how the JEDI ETKF system is working. So all of you guys know here, I think JEDI is great. And the partners that are in JEDI in their respective models, we are working with the NRL SAMI and we're working with this Neptune Falcon. And also we have a whole bunch of people that are in the space weather community moving towards JEDI. The WAM-IP and then the FE3, as well as the WACM-X and all of these different centers. So this is all more reasons to go in the JEDI direction, because we are going to be able to utilize a lot of tools that these other places are developing as well. So the ETKF cycling system looks something like this. It's pretty generic. You have an ensemble of forecast backgrounds. You have an ionospheric observation. You feed that into the JEDI DA framework. That ends up giving you an ensemble analysis. And I should also put in here, not only the ensemble analysis, but it also gives you an ensemble of model parameters. You then feed those into NRL SAMI as an ensemble, and then you can come up with your 3-day forecast if that's what you're shooting for. And you have a measure with the ensemble of forecast skill. If you're going for just the cycling, then you just feed that into a short forecast, however long your DA window is, and then that goes in the ensemble background, and then it goes around and around. So as I think I've already said, we've set up the JEDI DA frame. Oh, in this green box basically is this green box down here. And we have the specific implementations that we've been working on with this NRL SAMI, which I said before is a model we can't really share with the community because of restrictions. But PyIRI is, we have PyIRI output in the exact same grid as we have NRL SAMI, and it actually is a pretty good system. So we've got that open to the world, and we can set up our C tests and all of our fun stuff that hopefully breaks when PyIRI breaks. That would have also broken NRL SAMI, so that we can keep at the point of the spear of JEDI development. And then we are working on currently the Ionosons, the GPS Tech, and Cosmic 2. That goes in the IOTA, the ops space, and then the UFO and the ops operator, and those all feed into the LETKF. So that's sort of what the system looks like. I think you guys are all probably pretty familiar with that.
Well,
Okay, maybe you're not.
I wanted to ask you.
Okay, great.
Maybe get into the difference
Yeah.
between ETKF and LETKF.
Okay, so the LETKF has localization in it, okay? And so by localization, basically what you're doing is you're restricting only, so if you're at a particular state space, you are restricting only observations within, and I'm going to talk about physical localization because that's the way that I think about it, is that you draw a circle and you say, okay, say only the observations within 200 kilometers of that are going to have any impact on it. And so when we're doing our solve, we are only using these local observations. And the concept here is that if you do global, you end up with these spurious correlations, which can actually really mess up your system. So so that's why they went to local. They started with the ensemble Kalman filter globally, where you do this global solve. And when we went into the NWP world, they were like, oh, these spurious correlations are so large that it was killing us. Now, the thing is that when Dan Hodis started looking at the ensemble that we were getting for the ionosphere, the space is low enough dimensional. So, okay, so you can think of this several ways. If you had an infinite ensemble, you wouldn't have those spurious correlations, okay? Because then it would filter all those out because you have spanned the space completely. You never have an infinite ensemble. So that's why you have to do localization. Now, the thing is that's for high dimensional space. If you have a lower dimensional space, like what we have for the ionosphere, the thing is that there's this possibility that you can actually span the space with, 20 or 30 ensemble members. And thus you can actually do the global solve. You don't have the spurious correlations, and you can get a good result. And that's actually what they found, is that the ETKF for the system that was being driven by winds that were from these climatological wind and temperature models had this very high dimensionality. Now, the thing is that we're going to the situation where we're actually not driving it with these climatological models. We're driving it with an NWP model, which is very high dimensional. And that really does expand the dimensionality of the problem. And so the concept is that we may be able to get away with the ETKF right now as long as we're not driving it with Neptune. But once we get into driving with Neptune, we might have to go to the LETKF. It's a might. We don't know. We're still investigating that, but that's sort of the difference. Thank you. Anyone else on this?
But then I remember there was a study that's showing that localization doesn't work, right, for the space weather. I forgot it's cheating somebody, right? You did that work. It's I remember there was some right. There's some experiment you show the localization is scale is really big. That
I'm sure it is very large.
Yeah, it's very large, really big.
Thermospheric.
I forgot the exact.
Ionosphere.
Oh.
Yeah,
Yeah.
so I think that's only for TIEGCN.
Okay.
Yeah, it's very like low resolution model.
Mhm.
And it has, and that's it. This is model dependent. This whole problem is model dependent. If as the model gets more complex and higher dimensional,
Mhm.
then again, there's this possibility that you might go in. And you found with the TIEGCM, yeah, the LETKF doesn't work. What is nice is that the ETKF is like 6 lines of code. The LETKF is thousands of lines of code because that damn localization is the whole problem.
Mm.
And so, but what we did is because JEDI already has the LETKF, you just take your correlation length scale, throw it all the way across, and voila, you've got an ETKF.
Mm.
That's how we do it. So, yeah.
I'm just thinking that because for the field line,
Mm-hmm.
your correlation actually is not localized, right?
Well, it is localized. Now we're talking localized along a field line.
Yeah.
So now we've changed our space
Mhm.
so that as opposed to like a space horizontally, and maybe we still have a horizontal space, but now you have this long field line. And there are people that have been doing data assimilation with these what do they call them? Cylinders with spikes. I don't know if you've seen any of this. So that they have the local region has a spike which you can elongate and deal with weird shaped
Right.
relations.
I'm thinking more on the Gaussian grids, etc. But you are right. Your coordinate is along the field lines.
Right. Well, and that's what, yeah, when you break it and you go along in the Gaussian coordinates, you've lost it.
Yes.
You've lost the ability to do that.
Yes.
Which is why that's why I want to keep in the geomagnetic space. I've got 2 minutes left. Okay. No, it's my fault. I went way too long. Okay, so this is basically we set up the system. HODIS's ETKF was a non-operational DA system. He wrote it up in this paper. You guys can look it up. And this is our first sanity check where did the JEDI ETKF code to replicate these results. There were 84 tech observations. And over here on the left, we have the HODIS ETKF and we have the JEDI ETKF. And I think we're looking at, I should have blown this up. This is electron density at 300 kilometers is what we're showing. And the results are very similar. These systems actually solved, as I said, for parameter estimation. They had a solution for the F10.7. And we have here the analysis is actually blue. The background is black. And you can see that the HODIS system and the JEDI system are very similar. The difference between the two, the difference between JEDI ETKF and HODIS ETKF is very small differences here. And this is versus ensemble number. So we feel that the system is working quite well right now with this, this tech experiment. So the next steps with, so the JEDI ETKF system is to be used to not only give us an analysis state, but also for creating an ensemble, which accurately estimates the uncertainty of the model forecasts. Forecasting the ionosphere is very new, And it's very important, I think, for us as a community to try to keep a handlehold of what the uncertainty is of those forecasts. And one of the ways of doing that is with ensembles, and that's what we're trying to do. The next steps is experimentation with the real ionosonde assimilation, add in cosmic tune, ground GPS, formulation of the system, and anchor that I talked about, bake off of anchor in the ion density state space, and possibly design of a hybrid system. The future work is getting at this JEDI Atlas compatibility with geomagnetic grid. Discussions are ongoing on how we're going to possibly do that, and as well as ionospheric LATKF working on the geomagnetic grid. So the thermospheric DA. So I've talked, the Neptune Falcon DA has been used in development since 2020, and they have a 40 bar set, solver transition FY27. They're assimilating all the current NWP. We've got the Neptune MA, which will be run as the ESPC coupled system in the future when the NavGem ESP system goes away. That also is using a 40 VAR, but it's actually putting in some of these meteor radars in the SSMIS UAS. The Neptune HA, which is what I was talking about before, will run with current NWP operational OBS system plus these other observations is what we're shooting for. So the status right now is the Neptune HA model is running but not cycling with DA. We have temperature analysis increments at 61 kilometers with the Neptune Falcon. We've been testing the Neptune Falcon DA system in LETKF mode. We still use our DARPA Cepher NavGem HA LETKF system to validate our results. The next step is to raise the top of the MA and the Neptune Falcon DA, stabilize the cycling LETKF, and raise the top of the Neptune HA and LETKF mode and start filling in the HI observations. So that's what I had. 3:02, 2 minutes over. So sorry, everyone. I put too many slides in.
Okay, yeah, thank you. So if anyone has questions online or
I'm also going to be here for the next 2 days at the JEDI workshop. So if you want to, if you think of questions and you want to come and ask me, please don't hesitate. I'd love to talk. Everyone wants to
I
know.
just I do have one question. You know, the thermosphere, there's such little data.
Yes.
How much of a, I don't know, concern, or even into the middle atmosphere, there's
Yes.
almost nothing. How much of a concern is that, or is it?
It's a horrible concern. I mean, every single meeting I go into with anyone that's outside of that has any money, I say we need more observations. My sponsor is getting really pissed off at me. He's like, why do you keep saying that? It's because it's true. We don't have any observations. I don't know how else to say it. We've been saying it for 10 years. And we've got white papers on it, and we've got everything, and it's really going to be it's the problem of our community, and we need more observations. And I don't know. I just build my systems. I do it the best I can using the observations I can, and show them what it can be used for, and then we can run some Aussies to say if we have more, this is, you know, we'll be able to do better, and we'll be able to do maybe some of these things that you want. But yeah, it's
I think the satellite drag extractions show some promise in getting multiple, much more data out of the thermosphere, at least neutral density.
yeah.
The problem is getting multiple altitude shells and getting those companies to release data in a timely manner that can be used in this way.
Yeah.
And so,
And that's one of the reasons why with a lot of the work that Nick's doing is that as opposed to getting it from the sensors on the satellites, get it from trackers like ground-based trackers, because it solves two problems. One, it solves the huge problem, which is data latency and getting it to the getting it to ops. But the other thing is that you don't have to be beholden to these spurious networks around. Of course, the problem that you know is then what is the configuration and what is the you're making dirtier data
Yeah.
is basically, and I think a lot of it, what we're trying to do is see, maybe with that thousands and thousands, we can overcome that. I mean, that's what data assimilation is all about, is that, if you have a lot of it, you can try to extract any information that you can, and maybe because of just how much you have, it's going to be useful. So,
The other good news is Marty Malinzak's Nice Cube, which would be a replacement for Sabre,
yeah,
is
right.
getting some traction.
Oh, great.
So
There you go.
I think he got an H for that. So he does have money to begin
Yeah.
at least planning for launch.
And Sabre's been around for a long, long time.
Yeah, 2003 launch, something like that.
Yeah. It's been a workhorse for us. We
So
really love it.
this
And
is
you're incorporating Sabre. Yeah. Is there any of the observations that I have here did I miss anything that you guys are like, or,
Fabry Pro interferometers are
right.
possibly interesting for UV extraction.
Yeah, there's quite a few of them.
Yeah.
One-
Yeah.
Yeah, there's only a small number.
Right. And yeah, I remember you guys talking, and the scintillation products,
Yeah, I mean, that
is that
DA is a little tricky.
yeah. I was hoping someone else solves that for me, and I could just use that.
It's more like the data you want to get rid of.
Right. Yeah. But yeah. Okay.
I think the scintillation is another problem.
Yeah.
Yeah, what you can do with that data, and
Right.
could you, make a DA-like system that incorporates it just to do scintillation?
Yeah.
Hopefully this will be a main conversation of the next 2 days, the workshop.
Mhm.
What observations do we have? What do we need?
How can we get the information?
Yeah.
That Dave, I really like that figures.
The little figures that we go through.
Yeah, figure is a good plot showing which observation available. Love it because it's also tell me that which height is available, right?
Yeah, it's kind of that. I mean, because of the font size,
Yeah.
I can't get it right on. Obviously, I missed a couple, but you get relative areas.
But are those the same that, for example, Wacom, the WAM or Wacom X, are you assuming all the same observations or system dependent?
WAM, I think, can only do the bottom.
Not high enough, right? Yeah.
Yeah.
They're working on satellite drag through
Yeah.
Eric Sutton's stuff.
For Wacom X, not everything. Some of the UV and SSMIS we didn't do, but
Yeah.
and we haven't done satellite drag in
Well, you
Wacom X.
haven't done that. Okay.
Done Wacom X, but people have in TIGCN.
Yes.
So it's kind of, it could be put in. One other thing, for Sabre, there was this nitric oxide.
Yes.
Some people, I was involved with a paper in that, that helps control the cooling during geomagnetic storms. So it's actually potentially quite a useful.
Okay.
Oh, you were doing temperature
That's,
saber.
Yeah, we do temperature for Sabre. We've been doing temperature from Sabre forever.
I think that's one of the focus of Marty's CubeSat. I think it
Yeah.
depends what your
Yeah.
cooling is in your model, and if you have a good representation
Yeah.
for it to be useful.
And a lot of that is with these UVs, with the O into and the O into ratio. It's how good. We just put it into the model, and so it's really green. And how good is it? Is it good enough? That's why all of that has more research for us too. But you have the full chemistry, so you've got a lot better.
Then I think some of the observations are
Yeah.
a little bit tricky because there's some biases. It's
Yeah. Oh yeah.
like I think gold is biased relative to UV.
Mhm.
Like they have
Yeah.
some constant offset. So which is right.
Yeah. Yeah. Well, and there was gold offset from Sabre too. I think that.
That's Scooby.
Oh, that's
which is
Scooby. Okay.
untimed.
Okay. Oh, there you go. And yeah, exactly. And that's what I could put on all of these slides is bias correction.
Yes.
Every single one of these, I've got that
I
problem.
was going to ask you because I remember you said the model forecast sometimes also away from observation.
Yes, very much so.
So
yeah.
do you do bias correction online or you're?
It's a problem, and but basically we're so early on that there, well, for the ionospheric stuff, they had, I think there's a cosmic two, there's a relative, it's this is kind of getting outside. This is when I lean on my other people. But I think there's a cosmic 2 tech, which is a relative tech, and then there's one that's an absolute tech. And so if you go with the relative, then you can take care of the, you know, there's tricks that.
Absolute is after that. Absolute TC is after bias.
Yeah.
Right?
Yeah.
Absolute is after the difference bias the DCB.
Yeah. And so there's ways to deal with that, but no, it's a problem. You have to.
But I assume for the radiance part, it's more important, right?
It's definitely important for the radiances. And what we do down here in the troposphere with these guys is, since we have a variational system, is we have RBC going.
Yeah.
And we use our VAR-BC in order to inform. Now, there are analogous ensemble methods of doing bias correction, and we're going to have to start pulling those out and start working with it.
But I think even Saber and MLS on bias.
Yes, yes.
I think you guys do correction.
We do correction.
I think
Yeah.
you probably also did correction.
Yeah.
Yes.
But that correction seemed to be pretty like stable over the years. Like our guy Carl Hoppel did it, I think like 7 years ago, and then we've been able to use that and haven't had to change it much. So sometimes the bias correction can be that. Yeah.
So any other questions for Dave or anyone online?
If there's anyone online still. Oh, there's 12 others still. Wow, we didn't lose everyone.
If not, well, thank you again, Dave.
No problem.
Yeah.
Thank you so much for having me.